Greetings, innovators and leaders. This is AI for the C-Suite, your compass for navigating the exponential age. I'm your host, Chad Harvey, and we're here to bring you cutting-edge insights on AI tailored specifically for middle market organizations. Buckle up as we embark on a journey through the transformative world of artificial intelligence. Today, we're joined by Rohit Patel, Director of Meta Superintelligence Labs, where he's at the forefront of building next-generation AI models that will shape how businesses interact with AI. What makes Rohit unique in the AI landscape is his rare combination of deep technical expertise and a real-world business strategy experience. With a PhD in game theory from Northwestern and over 6 years at Meta, Rohit specializes in AI evaluations and agentic systems, essentially how to measure whether your AI is actually doing what you need it to do and how to build AI that can act autonomously on your behalf. Before diving into the technical side at Meta, he spent 3 years at Strategy & Co. helping private equity firms create value through data and analytics, giving him a sharp understanding of what actually drives business results. Rohit also founded QuickAI, a research lab focused on building innovative small AI models, and serves as a digital advisor to BayPine, a PE firm helping shape their AI strategy across portfolio companies. Rohit's known for making complex AI concepts accessible and actionable, a skill that's particularly valuable as middle market companies navigate this rapidly evolving landscape. Later this year, Rohit will be speaking at TechCrunch Disrupt, and today he's here to demystify AI for business leaders and share practical frameworks for deploying AI with confidence. Rohit, welcome to AI for the C-Suite.
Thank you, Chad. Good to be here. Thanks for having me on.
Absolutely. I am really looking forward to our conversation today. And I want to dive right in to something that is a little bit technical, but I'm hoping that you can make it less technical. And that's the concept of how math becomes language. And I want to dive into this because I think you can help executives and owners and CEOs understand and better grasp what they're actually buying and building when we're talking about AI. And I know you're passionate about this. So let's demystify this concept. I know that you often say that once people understand how generative AI actually works, they can get more excited because it's not as mysterious as they thought it was. So perhaps walk us through a little bit in a as non-technical a way as possible how mathematical equations actually become language and reasoning that we see from tools like ChatGPT and Claude and others.
Yeah, I'd love to talk about that. I think the more people see these large language models or AI as a black box, the less good it is for us in terms of adoption, in terms of making the right decisions, and figuring out the right use cases. I think as people understand how these are built and what goes under the hood, it makes it easier to make the right decisions about them and to figure out the right use cases where we should be using them or not using them. So let's talk a little bit about that.
Please.
And I think the question of how does math become language goes to the heart of what neural networks are. So I'm going to talk a little bit first about what neural networks are, and then we're going to see how they sort of give rise to this generative AI. So at the very core, right, like a neural network is really a huge collection of a deep neural network. It's a huge collection of regression equations combined with their interleaved with these sort of activation where you have some sort of discontinuity. And by discontinuity, I mean or necessarily non-linearity actually, where it's not just a linear function of something. So what does all of this mean really in terms of neural networks? So what is happening in a neural network is you put some numbers into the network and these numbers go, some transformations. Mostly you do a linear set of linear equation, ax plus b, and you do this transformation, and then you apply a nonlinear function to it. Sometimes the nonlinear function is as simple as if the resulting number is greater than 0, keep it as it is. If it's less than 0, make it 0. This is a nonlinear function that is very popular called ReLU. And then you apply the next set of ax plus b linear equations, and you keep doing that, right? And after doing a number of these, you get another set of numbers in the end. The key point I'm trying to make here is neural networks are basically you put a set of numbers in and you get a set of numbers out. That's what neural networks are. And the way that they are trained is, I'll give an example. Let's say you're trying to build a neural network that is, about classifying an object into, an apple and an orange or something like that. And as you're trying to do that, let's say you have the weight, the color, some characteristics of this object. So what you do is you record these characteristics as numbers on paper and you feed them to the neural network, and all these sort of math happens. And on the other end, you can have because it can only give you numbers. It can't really give you apple or orange. You're going to have to come up with some interpretation for what that output means, right? Like, so you're going to have to think about a scheme, an interpretation scheme of how you make it output something, because you're the one designing the neural network. Remember, right? Like you're the designer. So you come up with a scheme and you say, hey, like I'm going to make this neural network output two numbers, and I'm going to tag each one of these numbers with an apple and an orange. And the number that is higher, I'm going to assume that that is what the neural network is, intended for it to classify as. If the number that is tagged for apple, if number, let's say the first number is tagged for apple and the second number is tagged for orange. If the first number is higher, I'm going to assume that the network classified this thing as apple. Or, if the second number is higher, I'm going to assume it's classified as orange. And I think it's a simple scheme, right? Like it allows you to interpret the output of to a neural network, which can, again, only be numbers, so you can only get numbers out. It can allow you to interpret two numbers as, hey, the network classified this apple as an orange. The network doesn't necessarily have an understanding of what an apple is or what an orange is, but it's your interpretation that makes it so, right? Like, and now you can start to say, like, I have these set of equations that gives me these two numbers, and now I put in my information, and I have a network that classifies, right? Like, so that's kind of how neural networks work. Like, we haven't talked about how to get it to train. Like, just because you made it generate numbers doesn't mean it's going to give you the right numbers, right? Like, it should, when you put the information for apple, it should give you apple. When you put the information for orange, it should give you orange. And we'll talk about that in a second in terms of how it's turned. But at a high level, what I want to sort of first make a line on or baseline on is like, what's a neural network, which is, it's a number crunching machine. You put in some numbers and you get some numbers out, and you come up with some interpretation for what these numbers are to connect these things, these numbers, to the real world, and which gives them meaning, right? Like, and that's essentially what neural network is. And we're gonna talk in a minute to answer your question fully. We're gonna talk in a minute about what kind of interpretation do I come up with to make it generate language. So we're gonna have a discussion around like this interpretation, but it all starts with putting in numbers and getting out numbers. So that's sort of what a neural network is. Now, getting back to the point about how do we train them before we get into how language is generated. The way to train them is think about like the simplest thing you can think of, right? Like, how would you train them? You need some training data. You're going to have a lot of examples of input data for apples and oranges and the correct labels for apples and oranges. So you're going to have.
Let me ask you, just interrupt real quick. What's the minimum number of apples and oranges in this scenario that you think you need for training purposes? Because we hear an awful lot about the volume of data. And
Right. Yeah, no, that's a good question. And I think that really depends on the purpose. So here's an example, right? Like, if you want this machine to be perfectly be able to classify apple and oranges, and maybe you're inputting data around the weight, the color, the various characteristics of each one of these fruits, you're providing it a good set of information. But if you need a very high level of consistency, you're going to need a lot of apples and oranges, right? Like, and the reason for that is apples and oranges can have a lot of variety. There could be green oranges, red oranges. So basically, If you're looking for something that can classify the most common type of apple and orange and can tell you red apart from orange, that would be relatively easy to train, actually, right? Like you can have like 100 tagged examples, and that would do a pretty decent job. Um, but the moment you throw in a green apple in there and it's never seen a green apple, it's just gonna get completely confused, right? So the challenge really comes not so much from how much data you need in some absolute sense to train these networks, but more what is it that you're trying to achieve. If you're trying to achieve extremely high precision, you're going to need a lot of data that covers all of these various different varieties of use cases that may come at the neural network. Um, Maybe they don't perfectly cover them, but they should have good coverage, and that way the neural network can generalize to other cases that it may not have seen. Um, so I think that's sort of like it's kind of not a perfect answer to the question, but it's just setting out the parameters that determine what kind of sample size you're going to need to solve a problem like that.
That makes a lot of sense, and I'm interested here too. So I know we want to get to some other stuff, yet with this Apple example, I think this is a great visualization for the audience. So there's hundreds of varieties of apples out there, and we talked about, or you talked about rather, how you need a large sample size of each of those types of apples in order to equate that to the numbers in the system. How then does the system make the determination that this is a Golden Delicious versus a Honeydew or a Honeycrisp versus a Fuji versus a whatever when it's looking at all those types of apples in that apple category?
Yeah, so I mean, the model we're talking about isn't making that distinction, right? Like we're just talking about something that can classify. So if you need a model that classifies different types of apples, right? Like then you're going to have to, probably firstly, you're going to have to, do the smarter way to do it would be to feed it an image of the apple and let it figure out what apple it is. But then you're going to need a lot of images of different types of apples and the labels of those types. And then you're going to train this model on those images, like it will be a vision model. I don't really want to necessarily get too much into the image of the discussion because that it's going to end up being a much longer longer conversation. Not necessarily because there's something different about images. It's just that I think language is a good starting point for this discussion because we're LLMs are the thing that are driving a lot of the innovation these days. But there are image adapters sort of that you attach to them to give vision to these language models. But the core of a lot of these models is still language. So it's important for us to sort of understand what's going on there and how language is being generated.
Fair enough. Then let's get you back on track with your explanation here. We'll put the apples in a bin and set them aside for the time being.
We had sort of a neural network that was trying to classify an apple and an orange, and we had come up with a scheme for interpreting the outputs of neural network as a classification, right? And we want to train this. So to train this, we will need labels and data with labels. So let's say we have label data where we have a lot of data for apples and oranges, and for each one of them, we know which one it is. And what's the simplest thing you can think of for training this? And the simplest thing, at least that I can think of training is like, why don't I feed the numbers into the neural network, see what comes out, and adjust the parameters or the weights, as they are called, of my regression equations a little bit. So I change those numbers a little bit and see if I get the desired result or I move in the direction of the desired result. So what that means is, remember I had the interpretation, the higher number, if the first number of the two numbers was higher, I was going to say it was an apple, and if the second number was higher, I was going to say it's an orange. What if I moved all the parameters, all my numbers a little bit, or in some direction, or one by one? So let's say I moved one of them a little bit in some direction. And right now, let's say my neural network, because it hasn't been trained, gives me the wrong output. So I have a label and it's apple, but it's giving me the second number as the higher number. So I rerun this thing with slightly modified parameter, and the second number gets larger. So that's not the direction I want to go to, right? Like I want to go in the opposite direction. I want the second number to be smaller and the first number to be larger for this input data, this particular input example. So for that parameter that I just changed, for that weight that I just changed, I know that if I increase that weight, it's gonna make me go in the wrong direction. So I should decrease that weight, right? Like, and that will take me in the right direction, and it will increase the number for Apple. And that's kind of the gradient of that particular weight, right? Like there is the way that I'm describing isn't how we calculate gradients, but it's an intuitive way of understanding what a gradient is, which is if I change that parameter ever so slightly in a particular direction, is my final answer going to get me closer to what I want or further than what I want, right? And then you calculate the gradients of all of these numbers and you just move them slightly in the direction of whatever takes you closer. So in this case, I would decrease that number. And for each number I know, increasing or decreasing, does it get me closer? Does it increase my first number for this example or increase my second number, right? Like, or, and if I make all these changes, what's going to happen is I'm going to be ever so slightly closer to my goal. And so you can do this math very efficiently mathematically, and that's how models are trained. You basically move everything ever so slightly in the direction that you want it to go, and you just start with some random numbers, and you keep moving them. You're moving them in the right direction, and you stop when you stop seeing the progress on the correctness of your answers based on the labeled data. So that's kind of like how these networks are trained. So that was a little segue into how network was trained, but I'm just trying to sort of build up to how do we get to language from all of this, and so now we have a way, we have a neural network, so we have a way of training them, and we know we put numbers in them, we get numbers out, and we have seen at least one example of how we can use these numbers to interpret them into some real world thing, right? Like, so let's get to language, right? How do we use this to generate language? Since we can only do numbers, we're going to have to come up with some scheme to put language into the neural network in number format, and interpret the output numbers as words, because language is made of words. So let's do that. Why don't we continue with our apple and orange example and turn that into, instead of apple and orange, turn that into words. So, I wanted to have the model classify into apple and orange. So I wanted the model to output the answer apple or orange, right? That's what I wanted. Here, I want the model to give me words. So what I can do is, instead of making the model output two numbers, we can make it output as many numbers as the words in the language. Let's say let's sort of limit our vocabulary to, let's say, 100,000 words. So I can make the model output 100,000 words and tag each one of those 100,000 numbers. I'm sorry, and I can tag each one of those 100,000 numbers with a word. So there's a number, with the, and there's a number with for, and there's a number for label, and all of these. And I can interpret that whichever of these 100,000 numbers is the highest, once the numbers are generated, whichever is the highest, I'm going to assume that that's the word that my model gave me, right, as an output. And that works perfectly fine. In fact, that's more or less how modern language models work, actually. They don't work exactly on words. They work on tokens, which are kind of like words that are broken up a little bit. But for purpose of this discussion, they actually won't change much if we think of them as words rather than tokens. So let's assume that we're talking about words. Okay. So what language models do is they'll generate 100,000 numbers, and we'll interpret these numbers, we'll look at these numbers, we'll find the largest number, and we'll say, that's the word that the model gave me. So that's a good way to build a generative AI from basically a model that is only capable of giving you numbers. It's all about the interpretation. It's about how am I interpreting those numbers, what kind of interpretation scheme I've designed. So I have to design this and agree on the scheme ahead of time, right? Like I have to think through this before time. And this is the universal scheme used in all language models, so there's not like an exception right now. There may be some like sort of fringe models or architectures or things like that do it differently. But by and large, every model that we know right now follows this scheme where they will generate a large number of numbers and interpret each one of them as a token/word. So that solves the problem of making the model generate. So we have a generative AI now, but generating words is still not language, right? Like these models are very coherent. They can generate multiple words, entire sentences, or even write books, right? So how's that happening? And where are these words coming from? There's some way for, usually we give the model a sentence and then it gives us question and then it gives us the answer. So how do we feed these words into the model? And the way that works is basically you come up with an interpretation scheme for every word to feed into the model. So what you do is you assign every word a number. You can arbitrarily assign every word a number, or there are obviously much cleverer schemes in reality. But let's say we just assign every word a number, like A, is for one, like 4 is for 2, like whatever, and we just feed those numbers in. That's as simple. That's like the simplest thing I can think of. And that would work. You could then you would be able to give it some words and you would be able to make it output some words. So now you have a neural network that can take in language and give you language. And the challenge is it's going to give you gibberish because you haven't trained it yet. But it's capable of taking in language and giving you language. And now the job is to train it, right? Like, so and the way that they are trained is you have the corpus of all the data, on the internet, all the public data on the internet, and you give it a sentence and you make it sort of output the next word. And it goes back to our apple and orange example. What you're doing is you're changing the parameters of the model ever so slightly, so that of all the 100,000 words, the number corresponding to the actual word in that sentence is the one that is the highest, sort of like that's where you want to get to. And now you do this, trillions of times, and you get a model that is actually able to predict the next word in a sentence. So like it can complete sentences in a reasonable, nice way. So that's sort of like how you train these models. The output scheme is pretty that we discussed is pretty consistent with what's reality. But I did simplify massively the input scheme, right? Like I just basically gave every word a number, and that's not really how it works. But it is kind of how it works. In reality, you don't give an arbitrary number. You actually come up with a clever way of assigning every word a number that helps the model do a good job. And you don't give it a single number. You give every word a group of numbers, a vector, sort of like. So you say like, so there it can capture the richness of the word, right? Like a vector. And you still feed all of these in the network as you would feed in a neural network. There's nothing special about how you feed them. They're all just numbers. Even a vector is just a collection of numbers in the end. So that's sort of like what you do in reality. These vectors are called embeddings, and they are usually trained. So they're trained when the model is trained, often at the same time. So you don't pick an embedding. You train an embedding alongside the weights of the model at the same time. So that's sort of like how it works in reality. But I think for the listeners, this is probably just like a detail. I think it suffices to understand that we take every word, we assign it a number of some kind, and using some scheme or a set of numbers, and we feed it to the network. So now we have a network that generates language that is capable of predicting next words. So that's kind of like how far we've discussed so far. Like obviously that still doesn't answer questions. It just generates the next token, and we can talk more about how we go from there to actually a question answering system, which is a whole new world. But let me stop there. Let me because we do now have a system of generating language at least.
Yeah. All right. So with that fundamental understanding in place, this is not the first time you've gone through this explanation, and it's not the first time that you've gone through this explanation for people that don't play in your realm. So when you do explain this concept to leaders, to executives, and they get this foundational concept and this construct, how do you find that this changes their approach to their AI strategy and what they're looking to do? Does it reframe their thinking on this? And if so, how do you see that changing?
Yeah, I mean, I think so. Oftentimes, I have like I guess oftentimes when I'm explaining this, I have a white paper board or something in front of me, so it makes it easier. But I would say that, like, the first reaction is a little bit of disbelief that it kind of works. It's like it just seems like entirely too simple to have an intelligence, and so I think that's sort of like maybe the first reaction, which leads to a discussion about scale. So I think the explanation is a conceptual explanation for how a neural network works with this. So you're probably thinking a small neural network, and the way we trained it didn't sound too sophisticated either. You just kind of move numbers around. You start with a random set of numbers and you move them around till you get the answer you want on the data you have. And then the conversation goes into that one of scale, which is like, okay, so it doesn't really work if you have limited scale, right? Mm-hmm. Which is what you normally think of or intuit. But if you think about the scale of the modern neural networks that actually show intelligence, the scale is so massive, right? Like that they're able to. We're talking about several billion parameters. Even the smallest models, right, like that are capable of intelligence today, have a few hundred million parameters. That is still a very large number of regression equations, right? Like hundreds of millions of regression equations, combined with nonlinearities. So that's a very, very complex system. Mm-hmm. Training a system like this is incredibly hard. As much as it sounds simple in principle, like move the weights around, actually, to not end up with the model not learning, to not end up with areas where you just end up in dead zones, it's really complicated. So I think with all that effort and all that richness, you get the intelligence. So I think normally the conversation after this belief goes into one of scale and understanding of, okay, how this might actually work and make sense. But eventually it leads people to have a deeper understanding of like, hey, this isn't necessarily, there are a few things that become clear to people. One thing that becomes very clear to people once they really internalize this is, why do models hallucinate, right? Or what is even hallucination? Because that's often people's mind goes to. And then, if you understand sort of how this is generated, it's clear to you that because the model is trying to give you the most likely next word, it doesn't really necessarily have a conception of ground truth, right? Like what it is trying to do is, across a very, very large amount of data, identify patterns that are the most likely to occur in the real world. And more often than not, those patterns align with some real pattern that have already occurred, and that's when the model is not hallucinating, right? Like, so I'm actually very surprised that the model gets information exactly right most of the time, because what are the chances that the most probable likely information or answer for a question is exactly the correct number that was for that question, and not something in the pattern of the universe that kind of was close enough to that number, right? Like so. But then it's sort of clear that hallucinations are a very natural part of it, and I don't necessarily think this is a bug. It depends on your use case, but the usefulness of the model also comes from the fact that they can generalize. An hallucination is the model trying to generalize beyond the information in the training data. And if the model wasn't able to generalize, I don't think we would get intelligence in the first place. I think it's part and parcel of what you're trying to do here, right? Like it's the model's imagination. Another way of saying is it's the model's imagination to think beyond what was provided and to generalize on the world. So I think that's another sort of like understanding that really helps people. And that actually is very helpful in thinking about how we can use it in products and how people can think through. And last, I think maybe the most valuable conversation that this leads to is like a deep understanding of, if I'm looking at a use case, I now have the ability to see whether this AI can help me with this use case or not, right? Like, is my use case something that can be helped with these sort of patterns? And then people sometimes, really enterprising people, will have ideas that go beyond language. They're like, well, I can actually change the interpretation scheme to be very specific to my business and do this and that. And I'm like, yeah, you can. That people do that. Like, and that's actually a very powerful way of using AI, going beyond just off-the-shelf LLMs.
I think that's a great segue into a little more practical discussion for business leaders, because we're talking a lot about the fundamental building blocks of these models, yet there is absolutely an arms race going on to release these different models into the wild, and then businesses are trying to wrap their arms around what this means and how they deploy these different models and best use them. So let's talk a little bit about something I know that you're also very passionate about, an evaluation framework and foundations for that. I know that a lot of AI projects fail. We've seen that MIT study. It's got some flaws. There's other studies out there that talk about pilot projects failing and other projects failing. And I think your preconception here is that a lot of these projects fail because organizations don't start with evaluations first. And I'd like to know, from your perspective, what is an AI evaluation? What makes an effective AI evaluation? And why is it critical for the success of an AI project in business?
Yeah, no, let's talk about that. That's a very important topic, near and dear to my heart. So I think before jumping into evaluations, right, like we have a model, right? We were talking about models. We have a model that can generate language. So what you do is you take that and you turn it into an instruction tuned model, which is a model that answers questions, right? Like, and there's a whole process for that. Maybe we won't get into that. I did write like a few days ago and release a paper that talks about reinforcement learning for model training in detail. It's not exactly for a non-technical audience. It's for engineers and practitioners, and it's full of formulas. But I think the early sections of it talk about the need and the concept of it, that just about, the first 2 or 3 pages that anyone can read and understand.
Then we'll make sure that we drop a link to that paper in the notes for this episode so folks can access that if they really want to geek out.
Yeah, it's an academic paper, but I think the first few pages will be very helpful to just about anyone. So anyway, so what we're trying to do is we're trying to have these models and we're trying to have them do real world tasks, right? Like, and what we're seeing is a lot of projects are failing, and there's just two parts to that. The first part is like the standard like organization, like projects fail, technical projects fail in large organizations or medium-sized organizations, and there are a normal variety of reasons that have existed forever, right? Like that are not special to AI. Like maybe projects are not run by sufficiently technical people. Maybe there's just not enough technical depth in there. Or maybe there's just not enough understanding or commitment, or the use case was misidentified and any of that. But there are also AI-specific issues with the Gen AI or AI projects, and one particular AI-specific issue is with the past technology. You could look at something. Let's say you're building a software, right? Like you could look at something, you can see if it's working, right? Like you could, if you're building a new order checkout flow system or instituting a new ERP, if it's not working, it's going to be obvious to you. Your order's going to start failing. Like things are not going to work. You can click through the order flow system and see if you were able to place an order. Like if we can look at a website. With AI, it's not so obvious. What happens is because AI has this sort of, it's not rule-based, right? Like, so it can work very well in demos and then fail very spectacularly. It depends on the quality of the models, right? Like, and how well the models are trained. So things can look very sleek. The interface can be very sleek. It can work very well in some use cases. You can even play around with, and it can work very well. And then it can fail because the model didn't have enough ability to generalize. The underlying model was weak. So it's sort of like you have a very nice car, but and the polish is amazing, but the engine is very poor, right? Like, and there isn't a way for an executive to test the quality of a model.
It's exactly what I wanted to know. Is there a way to test that?
Yeah. So I think this is a key problem. The second problem is the quality of a model doesn't necessarily, what I call, there's something I call like a non-convex intelligence envelope, where the intelligence envelope of an AI model is not convex. It's jagged, right? Like for a human being, for example, if you expect a person that has, let's say this person has done PhD in physics, and that this person has some other skills, you can reasonably deduce that they'll be able to do some other task that may be in between those, right? You can be like, yeah, well, they're obviously a PhD in physics, they should be able to do this simple math problem or something like that. And you can make generalizations about intelligence and that isn't true for AI. Just because it can do one thing really well, something else that seems like a simpler job for humans or trivial for a person that can do that other thing of that level of intelligence may not work, right? Like it's not, and it really breaks intuition for people. People tend to generalize that it's very good at this, and therefore it should be also very good at this other much simpler thing, and that's not really the case with AI. And that creates a problem. The problem it creates is in businesses when you're implementing. You have a particular use case you need it to be good at. You want it to be good at something that you need it to do. And just because a model is better at generally doing other things doesn't mean it is good at doing what you think, even though your task may seem simpler. So there are two problems. One is it's hard to judge which model is better in the first place. And even if you somehow had a system of belief about which model is better, and you were like, no, that's a good model, and you're using that model, you don't know if that's really good for your use case. So that leads to a very special problem that didn't exist in projects before AI projects that we have to solve now. And the way to solve it is through building evaluations, right? And what an evaluation is at a very high level, at an abstract level, like imagine you have a space of AI systems, right? So they could be AI models, they could be agents, they could be any kind of AI system, right? And you're trying to compare two systems. And an evaluation is really a scoring method that says, you give me a task, you give me a set of tasks. And usually you define an evaluation for a set of tasks. You don't define it in the vacuum. You say, this is an evaluation for this set of tasks. And an evaluation for that set of tasks, basically what it does is it will rank those systems. It will give you a score for every system on how good that system is on that task. That's what an eval is at a very high level, right? And that's what you want for your business. What you want is to say, hey, and the good thing about evals is you can also rank human performance on the same scale. So that's the beautiful thing. So let's say I am a business leader and I'm about to do an AI project. The first thing I'm going to do personally is I'm going to build an eval that is able to rank AI systems, and I'm going to run it with my people and get a baseline of how good what is the score of humans on this task, right? On this eval. And evals usually have a score between 0 and 1 or 0 and 100, depending on how you want to interpret it. But it's usually a number, 45%, something like that. So once you have that number for humans, you start on your journey. You can make a decision ahead of time. You can say hey, what I want to deploy a system in production, an AI system in production, is, if my score of humans is 78% on this task, which means 78% is what humans achieve on this eval, I want my AI system to have at least 50% for it to be viable. Or maybe you might want a higher precision than humans. Maybe you want it to be 80%. Your task is very sensitive and you don't want to fail or whatever. Or you could want 90, 95, 100%. Whatever your business needs are, you can decide based on the eval what is your target goal for a functioning good system that you want to hit it. So that's sort of what an eval allows you to do. So that's what I would do. I would first build an eval, baseline it on humans, and then I would have a tool to say, okay, now let's start our AI project, and let's see where the first iteration falls on this eval. Like, what is my score for the very first iteration? And maybe the score for the first iteration is going to be 20 or something very low. And that's okay. Now you have a way of iterating on your system, continuing to improve it until it hits a bar that you're like, okay, real world tasks, this eval, it tells me my system is at this. So that's really what, in a nutshell, eval is. And we're going to, I think, talk about how to build it, what goes in there, nuts and bolts of eval, why should you trust it, and stuff like that. But let me sort of pause there on what an eval is at a very high level before we dig into it, and see if you have any thoughts on that.
Well, yeah, I do. I'm getting more questions from folks. There seems to be a growing awareness that there are third-party benchmarking standards out there for these different AI models. And I want to make sure that we're clear here when we're talking about these evals and the different types of systems, what, if any, relationship exists between what we're talking about here, which is very company-specific or programmatic-specific to organizations and individuals and tasks, and those kind of higher-level third-party benchmarking tests that we see and are hearing more and more about with the AI systems out there. Could you just maybe unpack that for a minute or two so folks understand the differences in what we're discussing?
Yeah. So if you look at the benchmarks that are available out there, they're sort of like, what they're trying to do is they're trying to define tasks, and they're measuring score on that particular task, right? Like, and if your task happens to be exactly that task or very, very similar to that task, you can use one of these benchmarks, right? Like, but the reality is every business is unique. I've never seen somebody in a business that is trying to do an AI implementation and some off-the-shelf benchmark is just the perfect benchmark for them, right? It may be a good starting point in some cases if your task is very similar. Like, you could be like, hey, like, let's start with the models that are good on this benchmark, but because it kind of has similar tasks to the one we have. Mm-hmm. But by and large, these benchmarks are doing the same thing. They're giving a score on a task, right? Like, and often these papers will also release human scores on these tasks as well. So actually, they're kind of well done. And I really like these academic benchmarks because they're really well done. They're well thought out. It's just that they're for that particular task, and your business isn't doing that task. Your business is doing whatever you need. And I would be hard pressed to find a business that is so generic that one of these tasks would just work for them. But maybe it does. So I think that's kind of like the key difference. You want and that becomes especially important given the fact that we talked earlier about how the intelligence envelope of AI models is non-convex. Like, it's not convex, so you can't really generalize. So that means if your task is different, you really should be looking at eval on your task.
Perfect. No, thank you. I appreciate that because I didn't want to generate any confusion and have people think that maybe they can just pluck, as you said, a benchmark test out there and say, oh, that's a perfect fit for what we've got, because it's not. So let's make this real here when we're talking about evals. Let's paint a scenario here, and you can change some of the facts if you better suit your answer. But let's just assume I'm the CEO of a $500 million manufacturing company, and maybe I want to implement AI for customer service. Walk me through, how is my organization going to build an eval system to achieve that purpose?
Yeah. I love this part. It's, again, like demystifying something that sounds complex, and it really is so simple. It's just like, it's not very hard at all to build an eval. So I think basically what you're trying to do is, you're trying to say like, hey, I'm going to build a system for customer service, right? Like, and my AI is going to start responding to queries from customers. How do I? So let's just walk through how to build this one, right? Like, I think that will give people a very good idea of how to build them generally. But this is a really good that you brought up. So I'm trying to sort of build an eval for this use case. So where I start is basically, an eval is three things really at a high level. What you're trying to do, think about what you're trying to do in an eval. You're trying to sort of give a score for every model. You're trying to say, is this model better than this model or whatever? How do you do that? What is a model? A model is a collection of weights, as we talked about before, right? It's a collection of numbers and a scheme, interpretation scheme, and there's no way to sort of rank these things, right, inherently, score them. What you can rank or score is the outputs. You can say, which one gives me a better output, really? So with an eval, the answer we're really trying to get is, hey, I give you some inputs. Which of these models gives me the better output for what I need, for the task that I have? And that's really the question. So to build something like that, first, you're going to need a set of inputs, a sample set of inputs to give to an eval. And then you will take all these models and you will generate outputs from these samples. So these are like questions or input questions, let's say, eval questions. So you have eval questions, you run it on all the models, you get the outputs from all these models, and then you see which ones are better. So the most important thing, first thing you need for an eval is the set of inputs. So we'll talk about how we get to that. The second thing is you have the outputs, you have some way of figuring out which one is better. So the second most important thing you need is a way of ranking the outputs. Like you still need to know, they've just given you a wall of text. Every model just gave you a bunch of text for every input that let's say you have 500 inputs in your eval. So how do you rank them? So that's the second thing you need, a ranking mechanism. And the third thing is once you know which outputs are better, worse, or you have a score, you have to aggregate that into a single number. So you need a scheme or a metric or some mathematical formula that takes all of this and reduces it down to a number that you can then compare with human performance. And so those are the three components of an eval. So we'll talk about how to build each one of these. But those are very simple three components, right? So let's talk about the input first. Like, where do I get my inputs? And the best place to get inputs is real data. So go into your actual customer conversations and pull out 500 conversations or 1,000 conversations. I recommend 1,000, but 500 is a pretty good number. You can get reasonably good confidence intervals with a 500 sample, so it's not a lot of effort.
We're talking about recordings or transcripts of those conversations, right?
Correct. Recordings or transcripts of those conversations. And I was thinking more, in a chatbot setting, you probably have text,
okay.
but, from customer chats. But either way, like you basically have text of these conversations and you pull them. And you take 1,000 of those or 500 of those. And that's your input data, right? Like, so you take those questions and you feed it to the AI and you get the answers. Now, the beautiful thing about this particular situation is you already have human answers. You just pulled 500 real conversations, so you don't need to go rate it on, run it on humans again. You already have human answers. So you have sort of like a human responses already. Then you run these questions through AI and you get AI responses. So now you have a collection of responses from humans and AI and so on and so forth. And now you can proceed in many different ways. So this is a whole science around how to rank or rate responses by AI to build an eval. I'm going to talk about one of the simpler ways, and then we're going to discuss briefly some other more sophisticated ways of doing it. A simple way, the simplest way I can think of is, let's say you have 10 models to evaluate. You can give pairs of these responses to another person to say which one is better, right? You can send it to people and you can just say like, hey, here are two responses from two different models, which one is better? And they can rank it. And they can also, you can mix in the human responses, the real human responses in there as well. So model responses get ranked with, you can just treat the human responses as response of another model, right? Like, so the rankers don't know that this is coming from a human because that could introduce bias. And they were just saying this is a better response. So you have now a ranking of responses, and then you can combine all of those into a score using, either you can use ELO scoring, like how it works in chess. You sort of each time a response wins against another response, you imagine they won a chess game, and so you can combine the scores and get a ELO rating, same as chess players, or you can use something called the Bradley-Terry. Either is fine, they work fine, and you get a score for every model if you average it over a lot of chess games or a lot of responses, right? So that's one way of getting an eval, and in there somewhere is going to be your human, right? Like, or collective of humans. And that's going to tell you which model is where compared to humans, right? Like, and that is end-to-end how you build an eval. But there is an issue here, which is it seems complicated, right? Like, and I know we're sort of running up on time, so I'm gonna keep it very brief. But it seems complicated, right? Like you're asking people every time you run a new model, you're gonna have to go to humans and have them rate it. The cool thing is these days you can just have another AI model rate them, right? Like you can ask an AI model which is better, and they're reasonably good at picking the better of the two options. You can go further and you can have criteria for how to rate a better response, and you can refine the criteria for how to rate a better response before you give it to the AI model. So you can give it the two responses and you can give it the criteria and you can say, based on this criteria, tell me which one of these two responses is better. And that gives you an automated end-to-end process that you can run in under half an hour that will give you, so it's upfront work to pull the information to set everything up. It might take you a few days of work. But once you have it set up, you have an eval that is so powerful that any system you deploy or iterate, you know exactly where you stand. And because it is all coming from your real data, you can be assured that the performance in practice is going to be consistent with because these are responses to your real questions compared to real human responses. This is not some fake made up environment, right? Let me cap that off by saying like evals are super valuable, super important. I wish more projects started there, and I think that's a natural and a good starting point. For making sure your project is successful, just by knowing where you stand. This generally knowing where you stand is true, whatever project you do, but in this case, evals is how you achieve it.
Okay. I would love to unpack that more because I think you talk about these being known as judge-based evals. As you mentioned, though, time is getting short, and I do want to get to a couple other items here before we wrap today. Everybody is talking, and I use the word frothy a lot. Everybody is talking about agentic AI. It's a very frothy topic. Everybody wants to know about agents and agentic AI and business applications. So I want to segue into that a little bit here. And when we're talking about agentic AI, from my perspective, we're talking about AI systems that can act autonomously or semi-autonomously. And you, I know, work on training foundational models to be good agents. I'm using air quotes for our audio listeners. And I'd like to know from your perspective, how should middle market companies be thinking about agents and AI agent and agentic systems? And what is the difference as a follow-up to building agents on top of existing models versus what you're doing?
Yeah,
because I think you're taking a different approach, correct?
Yeah, no, I don't. I don't think it's a different approach. I think that the idea is that the models need to be good at being influenced. It doesn't. It doesn't necessarily. So, what agents? What are agents? Agents are basically you're taking a model and you're giving it more tools, ability to interact with the world or fetch information from the world, you search online, and you have multiple models that work together to achieve something. So that's what agents are in a nutshell, where you're extending the model's capabilities from just being able to do language to more things. And the way you do is you make the model because the model can only output numbers and you can only interpret those numbers. You make the model output, API calls, or you make the model output, cursor movements or things like that. And then based on that, you sort of interpret that and you say, like, this is what the agent wants. I'll fetch that information and I'll put it in the input of the model once I have that.
That sounds really complex.
Not really, if you think about it. Like, for example, if you have an API for, so let's take a very simple example, weather, right? Like, you have an API for weather, and the API call goes like something like you just send it a blob of text. You say get weather day to day, comma Miami, comma 4 p.m. forecast, right? Something like that. And the weather API is designed to take this blob of text in this specific format and just return another blob of text in a specific format that just actually gives you the weather, like precipitation probability this much. So these APIs are fixed. They're able to take these texts and respond with texts that are formatted in a particular way. And the simple thing for the model to do is you train the model to actually output that text that you're going to send to the API. So the model then outputs the text. and you understand the format. So every time the model outputs that, or you can even tell the model to, before it's going to output the API text, just let you know that it wants to do that or something like that. And you just parse it, and you know that it's trying to do that. So you haven't done anything different. The model is still outputting text. You've just trained it to output the text in the format of the API for that particular call. And then you make the call using standard software that you normally would. You get the response that normally would using a software, any kind of request in package in any software. And then once you have that information, you put it back in the context of the model. So you feed those words back to the model. So the model understands the structure. So the model is like, oh, okay, now I've got forecast for this. So it's actually quite simple. And but the thing is, in this example, you have to have the model train the model to be able to use this API, right? Like the model has to know and understand this. And that sort of, and you can generalize this a little bit more, like Model Context Protocol will generalize this to not so that every model doesn't have to learn every API in the world. So you sort of standardize things a little bit more in formatting. So you learn that particular formatting, and then you can call many APIs and so on and so forth. But you still need the models to be trained to do some of that. And I think that's sort of, I don't think this is an onus on necessarily the businesses. This is more about like what the labs are doing. Even though if you are a business and you're a big enough business that you can train your own models, you can actually train them to be very good at your APIs or your tools within your business, right? Like it's not as easy, but it's certainly doable. So I think that's sort of like how the agent world is in terms of like, for execs, what they should be thinking when they're thinking of agents. I think they should be, like thinking of them as any other AI system. Like build an evaluation. An agentic system is a detail of how you make the AI more capable and richer. And once you have an evaluation about how it's doing end to end, then you can sort of make the agent better or richer.
Okay. No, I appreciate that, because I do think that there's a substantial amount of interest out there about AI agents, and I don't feel like we've achieved the full promise or potential of them yet. We're just scratching the surface. So with that idea in mind, as maybe one of our last topics here today, you're in a unique position. I'm sure you're talking to your counterparts at other frontier labs. I know you're working on very cutting-edge tech. I don't want to get too far out over our skis, as the saying goes here. So maybe as we're looking out over the next 6 to 12 months, what should executives and leaders be preparing for in terms of AI capabilities and business impact? Do you have any thoughts on that?
So my thoughts on that are, and again, as I said, these are more of what I think is like the capabilities of models are constantly increasing. The space is moving fast. But there is a very high level or good level of base intelligence that the models already have to achieve a lot of the business tasks, right? Mm-hmm. Like, so I don't know how much, at some point it becomes more important that the models are tailored to do the tasks that your specific task well, than that they're generally a little bit more intelligence, right? Like, so I don't know how valuable it is to chase every new model update and do it if your task is very niche. If your task is very niche, I would recommend to focus on making sure the model, your orchestration works really well for that task. And yeah, I mean, you should update models or upgrade models, and maybe that will give you some improvements in the task. But it's also not necessarily the most important thing to care about. Now, will more capabilities unlock new tasks going forward? I think yes. And that means that the surface area of things that people can achieve will increase. But there is just an enormous amount of things you can already do. And I think we're in a situation where the technology is underutilized for what it is, even with no further sort of like, I think even with no further innovations, we would have a long time ingesting this into.
Well, and you touched on the issue of value here, so let me ask you this as well, because I know you've got some experience in your advisory role with BayPine. What patterns, if any, are you seeing in terms of value when you're evaluating what type of AI investments are going to create and drive real value? So from a private equity perspective, from a leadership perspective, are there any, again, patterns there that you're seeing?
Yeah, I mean, I would say like there isn't like this isn't something that is like a surprising thing, right? Like I think what people are trying to do is people are trying to find places where they can automate tasks and minimize, which is what was expected and which is what we're seeing. So people are able to, I mean, sometimes people find surprising and interesting applications. Oftentimes it's simple stuff, that is just minimizing the number of like sort of like the amount of work that people have to do in organizations for summarizing, or some people are trying to use them to get a sense of, some media agencies are exploring or like how do we prepare in an automated way reports for how our employees, what kind of matters our employees worked on for a legal firm or a PR firm, right? Like what did we work on that we can send reports to our clients that could be more detailed than manually preparing, 4 hours worked on this so things that are just like tedious in nature for people to do can be automated very easily, and AI can look at all the work you did and very easily summarize like, hey, like this employee worked on these things, and then you can send it to the client. It's like, hey, we billed you for X hours. That's an example. So I think there are just or internal systems that allow you to mine internal data, RAG-based systems, and then answer questions. That's also another thing. So and then people are obviously have been for a long time. This is not new to generative AI. Have been for a long time trying to use AI in the field to do things and stuff like that. But that hasn't stopped, and that is continuing. It just has accelerated because now we have more.
Sure. Rohit, we're just about at time here, and I want to thank you so much for sharing your insights with us today. This was a fascinating conversation for me, and I usually ask a question at the end about, what's one piece of advice you'd want to give to C-suite execs. I don't want to do that with you because I think your passion for what you're doing comes through. So what I want to ask you is, what are you most excited about in the world of AI right now from your vantage point?
Gosh, that is a lot of things, I would say. But I am excited about seeing how far we can push the models to be more and more intelligent, to see like how well can we do. And there's just a lot of things to explore. I think we have a kernel of intelligence, like in the entire internet was built on packet switching as the kernel of something small, or the entire computing revolution was built on a transistor as something small. And so I think what I'm excited about is we have a kernel of intelligence. What are the amazing things we're going to build out of that level?
I think that is a fantastic place to leave the conversation, with the possibility of what are we going to build next. So wonderful. For our listeners that want to learn more about you, about your work, get in touch, what's the best way for them to do that?
I mean, I think I post on LinkedIn and Medium. I have a number of followers on both platforms. Mostly my posts are about, either what the future of AI is going to be like, or very technical for the technical audience. They skew two ways. So, yeah.
Very good. So track you down on LinkedIn or on Medium is what I heard. All right. Very good. Well, and for our listeners out there, thank you once again for tuning into AI for the C-Suite, where we're committed to helping middle market leaders thrive during the exponential age. If you found value in today's discussion, be sure to subscribe to our podcast, follow us on all the socials, and visit our site, aiforthec-suite.com. Join us next time as we continue to unlock the potential of AI for your organization. And until then, keep your algorithms running, your leadership evolving, and your AI in check. Thanks, everybody.